This is lecture 22 in BBSP 610. It's the final regular lecture. It's going to be a review of the class thus far and trying to give you a general overview of what steps you should take when you have a data set that you want to analyze, and in particular how you answer what's probably the most common question I get in this class: that, wow, you've taught us all these different statistical methods. How do I know which method to use in which situation? So before I get into that, first, just wanted to give a general overview about, given a new data set, what are the steps that you should do in order to analyze it. The first thing you'll want to do is typically define a response variable in your predictor variables. If you're comparing a drug to a placebo, then the response variable would be whether or not they experienced pain relief, whether or not their cholesterol went down, whatever the effect the drug was supposed to do, and the predictor variable would be whether they got the active drug or the placebo. Or if you wanted to see if smoking affects lung cancer, whether or not they developed cancer would be the response. Your predictor would be whether or not the person smokes. Then you should figure out whether each variable is continuous or categorical. As you recall, continuous is a numeric value that can take a continuous range. A categorical variable is something that can only assume a finite number of values. For example, if you want to see if a drug affects pain relief and whether or not they got the drug, the active drug, or the placebo, that's definitely categorical. If pain relief were defined as either pain relief or no pain relief, then that would be categorical as well. If you asked people to rate their pain on a scale from 0 to 100 or something like that, then the pain rating would be continuous. And the next step that I very strongly recommend, and that I hope to see in your final projects, is before you do anything else, you should plot a response variable against each predictor variable using box plots or scatter plots. This will help you answer the big picture question: is there a relationship between these variables? What type of relationship? What can I expect to see? It's also a good way to check to see if there's bad data in your data set. After doing all that, then the next step is to decide which test or which method is appropriate. So how do you know which test to use? It can be a difficult question to answer in general. Sometimes there's not a clear-cut correct answer, but it is determined to a large degree on what types of variables you have. And so the important thing to know is what questions you're trying to answer with each test or method, what assumptions they make, what are the advantages and disadvantages. The first test we discussed in this class is the one-sample t-test and corresponding confidence interval. This is when you have only one variable. Say you collected the heights of a bunch of people, and you're not looking to predict or explain these heights, nor use those heights to predict or explain anything else. You just want to do a study on height. Well, you can use a one-sample t-test and confidence interval in this case, and you can use it to test the hypothesis that the mean height is equal to some value. It's pretty rare to do that type of test, but you can. When you have one sample, what's much more common is to use it to find a confidence interval for the mean. Pretty much any paper where you report a mean, you will want to report a confidence interval or a standard error to give you some type of idea of the uncertainty of this estimate. The next test would be a two-sample t-test, which you can think of it as when you have a situation where you would want to use a two-sample t-test is when you have two variables, a continuous response variable and a binary predictor variable. Do you want to know, does case status affect whether or not you're a case or control, determine how likely it is that you have pain? Does the drug or the placebo affect your cholesterol level? Things like that. And the null hypothesis is that the mean is the same in both groups. The alternative hypothesis is that there's a mean difference, or another way you can look at it is that the quantitative variable and the binary variable, or I shouldn't, the alternative way to formulate the null hypothesis, rather, if you have a quantitative variable and a binary variable and you want to test the null hypothesis, they're independent of one another, there's no association between the two. If you can reject the null hypothesis, the means of the two groups are equal, that implies that the mean of the response variable varies according to the value of the predictor variable so that they're not independent. And when doing two-sample t-tests, you can do either paired or unpaired t-tests. If, in order to use a paired t-test, every case must be batched to a control, or more generally, every observation in one group has to be matched to the other group. In particular, if the group sizes are unequal, then you can't use a paired t-test. A paired t-test generally will give you better power and better results if the pairs are homogeneous. If they're not homogeneous, then you can get reduced power or spurious findings. So next, let's consider counter proportion data. You can think of counter proportion data as repeated observations of a categorical variable. If we survey 400 people and ask them who they plan to vote for in the presidential election, you will have 400 observations of you'll have 400 observations of a binary variable that either they're going to vote for Hillary or they're going to vote for Bush or Trump or whoever ends up winning the Republican nomination. One way or another, it would be a binary variable with two possible categories, assuming that you don't consider third-party candidates. So if you only observe one binary variable, then you would do a one-sample proportion test or confidence intervals. Like the one-sample t-test, you'll mainly use this to find confidence intervals for the proportions, but occasionally you may want to use it to test hypotheses about a single proportion, for example, whether or not the president's approval rating is over 50%. And a closely related test is the one-sample chi-square test. It's more general than the proportion test because it's when you have one categorical variable that may have 3 or more levels, you will pretty much only use the chi-square test in the situation where you want to test the null hypothesis, the proportion of observations in each level are equal to some specified value. You might use it in genetics, for instance, test the null hypothesis that a certain trait is Mendelian or recessive or something like that. It gets more complicated when you have two categorical variables, since there's a number of different methods that you can use. Two-sample proportion test, chi-square tests, which may or may not have simulated p-values, and Fisher's exact test. Don't stress about this too much, because the vast majority of the time all of these methods will give extremely similar, if not completely identical, results. But I'll briefly go through the pros and cons of each of these tests in the upcoming slide. The most common test that people use when you want to compare two categorical variables to one another: does drug/placebo associate with pain relief/no pain relief, two categorical variables. You can use a chi-square test, test the null hypothesis, they're independent. It's far and away the most commonly used. The only real drawback is that it can give unreliable results if the expected cell count is very small. In my experience, even when the expected cell count is small, usually the results it gives are correct or very close to correct. But if you're submitting a paper to a journal, a reviewer might yell at you in this case. An alternative version is the two-sample proportion test, which is like the chi-square test, but it can only be used when there's two binary variables. If any of the variables has 3 or more possible levels, then you cannot use this test. And it possibly avoids some of the issues with small cell counts and chi-square tests. It has some issues of its own. And for this class, I don't think R will even compute this test directly or require some non-standard software, so in this class you will probably never use it. Next test to consider is the chi-square test with simulated p-values. You would use it in the same situation as the regular chi-square test. The advantage of the simulated p-values is that it doesn't assume a normal distribution, which can possibly give you better results if your sample size is small. It doesn't get used very often, so reviewers might raise some eyebrows if you use it, and it has some slight reproducibility issues in that the p-value will be slightly different each time you run it. It shouldn't be very different, but that can bother some people. Next test for categorical data is Fisher's exact test. You will use it in the same situation as the chi-square test. It also doesn't assume a normal distribution. It will give you an exact p-value, and it doesn't get used as much as the regular chi-square test. That's mainly for historical reasons. Before we had computers, Fisher's exact test was virtually impossible to compute, whereas the chi-square test was relatively easy. Nowadays, with computers, I think Fisher's exact test should be used a lot more often than it is. The biggest downside is that if you give it a large table, it can be really slow and can sometimes cause R to crash because it uses too much memory. So the next statistical method that we discussed is regression. It's mainly used when you have two or more quantitative variables that say you want to predict, does the speed of a car affect the distance it goes before it stops, was an example we used in some of the previous lectures. We have two numeric variables. You want to know, are they associated with one another? You'll designate one variable as the response variable, usually a variable you want to predict using the other variable, and you can test the null hypothesis the response variable is independent or all, or some of the predictors, and you may want to use it to predict the response as well. So there's several tests associated with the regression model. The F test tests the null hypothesis that all of the regression coefficients simultaneously are equal to 0. This is usually equivalent to testing the null hypothesis that the response is independent of all of the predictors. If you're trying to predict the risk of lung cancer based on smoking, BMI, socioeconomic status, etc., the F-test is testing the null hypothesis that none of the variables you measured in your study are associated with the outcome, and there's no confidence interval associated with this test. And for each regression coefficient, there's also a t-test and a confidence interval. It'll test the null hypothesis that a specific regression coefficient is equal to 0. And so in principle, you can use it to test the null hypothesis that x and y are independent if only predictor x is included in the model, or to test the null hypothesis that x predicts y independently of the other x's. And it'll also give you confidence intervals for the regression coefficients, which are of interest in some situation. I'll go back to this soon, but the third bullet point, note that it does not test the null hypothesis that x is independent of y if you're in a multiple regression model. It only tests the null hypothesis that x doesn't give you any information about y given the other x's, which isn't exactly the same thing. And you can also calculate confidence intervals or prediction intervals for regression predictions. A confidence interval for regression prediction is chosen such there's a 95% probability that will contain the mean value of y for a given x, and a 95% prediction interval is chosen since there's 95% probability that it will contain the value of a single observation of y given a value of x. Most of the time in practice you'll use prediction intervals, but occasionally you'll want to do confidence interval. In the cars example, it would be a confidence interval would give you a 95% confidence interval for the mean stopping distance of all the cars. that have a speed of 25 miles per hour, whereas the prediction interval would give you a 95% confidence interval for the stopping distance of an individual car. And in theory, you could use these methods to test the null hypothesis, the mean value of y for a given x is equal to a specified value. Almost nobody does this in practice, so don't worry about it too much. Final method that we considered was analysis of variance, or ANOVA, which is used when you have a quantitative response variable y and one or more categorical predictor variables, typically that have 3 or more categories. If they have 2 categories, you can use ANOVA, but a t-test is more common in that case. But if there's 3 or more, then you'll need to use ANOVA. And it tests the null hypothesis the response variable is independent of the categorical predictors. Well, some pitfalls and some important things to keep in mind when you use these methods is that I strongly recommend that you graph the data before performing additional analysis. For starters, it'll help you see if there's outliers or other bad data, and it'll just help you see the general pattern in the data, what type of model is appropriate. And also, I'm going to put this in big bold-faced letters, hoping that people don't make this mistake this year, even though every year that I've taught this, it's been the single most common mistake on final/final presentations, etc. If you have a list of possible predictors of an outcome and you want to say which predictors are associated with the outcome, you cannot just put them all into a big multivariate regression model and see which coefficients have a significant p-value. The multivariate regression model tests the null hypothesis. Does x1 give you additional information about y given x2, x3, x4, and x5? That does not tell you whether x1 by itself is associated with y. So the correct approach is to do univariate analysis first, is t-tests, chi-square tests, univariate regression on each predictor individually, and then do your multivariable regression model. Because it's quite common for a predictor variable to be strongly correlated with a response variable, even though it's not significant in a multivariate regression model. And that's pretty much all I have to say for this review.